Hello everyone. In this video, I'm going to talk you through some of the typical units of concentration we will be encountering in this module, and more generally the ones that you will be encountering if you ever work in environmental chemistry. So I've got a presentation that I'm going to share right now, and let's make a start. So when describing environmental processes, it is very important that we know how much of the chemical we're studying we actually have. What is the concentration of that chemical in the environment? Because toxicity, legal limits, they are all related to not how much of the chemical you've got, but rather, okay, how much of the chemical you've got in related to the sample you have. What is the concentration of cadmium in that soil sample? What is the concentration of magnesium in a water sample? What is the concentration of nitrogen dioxide or carbon dioxide in an air sample? And we have quite a few types of units to describe those concentrations. In aqueous solution, you probably are familiar with the concept of molarity, moles per liter, and that's very popular concentration unit in chemistry. Because we are working with very low concentrations, the chemical might be very toxic, but it's typically found in small quantities. Then instead of talking about moles per liter of substance, we talk about micromoles per liter or nanomoles per liter. So micromolar concentrations and nanomolar concentrations are more common employed in the literature and in scientific reports describing the concentration of a chemical. Other units you can use when describing the concentration of a particular analyte of a particular compound is mass of the compound per total mass of sample. This is very common when working with soil samples. So nanograms per kilogram or micrograms per kilogram are very common units to describe the concentrations of particular samples in the particular chemicals in a sample. A very common unit used in water pollution and when we're working with water samples are the mass of the compound, the mass of the analyte you're interested on, the chemical you're interested on, potentially a pollutant, per total volume of sample. So milligrams per liter, micrograms per liter, or nanograms per liter. The amount of chloride in a sample in milligrams per liter, the amount of potassium ion, sodium ion, chromium 3, cadmium 2 in micrograms per liter, milligrams per liter, nanograms per liter. Other popular concentration units using environmental chemistry are ppms and ppbs. ppm stands for part per million, ppb is parts per billion, and it's a US billion, 1,000 million. And what the unit is describing is not exactly what you have, but the relationship between the two units that they make that part per million or that part per billion. If you have one soil sample contaminated with 1 ppm of chromium 3, what the unit is telling you is, if you imagine your soil sample divided in 1 million small pieces, one of those pieces, one of those units would be your chromium. Parts per billion, if you have 1 ppb of manganese in your sample, if you imagine your sample divided in 1,000 million little pieces, 1,000 million units, one of those units would be of your manganese. So how do you convert from ppbs and ppms into some of the previous units I've mentioned, like milligrams per kilogram or milligrams per? Well, for soil pollution, you find two units of weight that are 1 million units apart. So for example, milligram per kilogram a microgram per gram. There are 1,000,000 milligrams in a kilogram, and there are 1,000,000 micrograms in a gram. So 1 ppm of cadmium is the same in a soil sample. It's the same as saying your sample has 1 milligram per kilogram or 1 microgram per gram of cadmium in it. For water sample, we start from the same place, milligrams per kilogram. So 1 ppm of, if your sample contains 1 ppm of sodium ions, it has 1 milligram of sodium ions in 1 kilogram of water. And we can use the fact that we know that 1 liter of water weighs 1 kilogram because of the density of water to convert that to milligrams per liter. So 1 ppm of sodium ion in your water sample are 1 milligram per liter in your water sample. For pp's, there are 1,000 million micrograms in 1 kilogram, and 1 kilogram of water is 1 liter of water. So ppb's are micrograms per liter. For air pollution, the things are slightly more difficult, and that is because a popular unit in measuring air pollution is cubic centimeters per, ppms. And another popular unit in air pollution are micrograms per cubic meter, and you will see many environmental standards, air pollution standards set in micrograms per cubic meter. And the relation between the two of them is specific to the gas you're looking at. So 1 ppm is 1 cubic centimeter per cubic meter. But how much does a cubic centimeter of a gas weighs? Well, it depends on two things. It depends on the weight of the gas, and it also depends on the temperature, because gases expand with the temperature. So you will have fewer molecules of the gas at a higher temperature if you have 1 cubic centimeter. And at low temperature, when the gases condense and contract, you will have more of those molecules, more of that gas, more weight of that gas in a cubic centimeter. So we need to look at a specific example to see how we work out how many micrograms per cubic meter you have when you have 1 ppm of a particular gas. And in this example, I've chosen NO2, nitrogen dioxide. Two things you need to know, or we need to set up, is the temperature of the gas and the pressure. Typically, you look at atmospheric pressure, 1 atmosphere, and what is considered room temperature, 25 degrees to 198 kelvins. So how many micrograms per cubic meter are in 1 ppm of nitrogen dioxide? 1 ppm of nitrogen dioxide are 1 cubic centimeter per cubic meter of nitrogen dioxide. So now the question is, how many micrograms of nitrogen dioxide are in 1 cubic centimeter of nitrogen dioxide? To find that out, you need to use a couple of equations, both very common in chemistry and physics. One is the equation that relates the weight of a gas to the pressure and the volume. And that is the ideal gas equation. It does not specifically tell you about the weight in grams or milligrams. It tells you about the weight in moles, but that can be converted later. So to know how many micrograms are in 1 cubic centimeter of nitrogen dioxide, we need to first know, using the ideal gas equation, how many moles of nitrogen dioxide we have in 1 cubic centimeter of nitrogen dioxide. P is pressure, V the pressure of the sample, V is the volume of sample, the number of moles that we don't know, R is the ideal gas constant, and T is the temperature and given in Kelvin. The ideal gas constant is tabulated, is 0.0821 atmospheres per cubic decimeter per mole per Kelvin. And what I've done here is, because I don't want to have the cubic decimeter, I'm interested in all my units coming out in cubic centimeters. I've converted cubic decimeters into cubic centimeters. And the way to do that is just by knowing that there are 1,000 cubic centimeters in 1 cubic decimeter. So I've converted 82.1 is the R constant converted to atmosphere per cubic centimeter per mole per Kelvin. So we've got the equation, and we rearrange it to leave moles as your unknown. We know the pressure is 1 atmosphere. We know we have 1 cubic centimeter of nitrogen dioxide. We know the value of R, 82.1, and we know the temperature, 298 kelvins. Doing those calculations comes up with this value. 1 cubic centimeter, in 1 cubic centimeter of nitrogen dioxide, there are 4.08, 10 to the minus 5 moles. So we are in one step closer to our goal, which is how many micrograms of nitrogen dioxide you have in 1 cubic centimeter, but not quite there, because moles are not quite micrograms. We need to convert our moles of nitrogen dioxide into micrograms of nitrogen dioxide. And we can do that by using the equation that relates moles and mass. And the equation that relates moles and mass is mole equals the mass divided by the molecular mass. The molecular mass we can get from a periodic table, and for nitrogen dioxide is 46 grams per mole. 1 atom of nitrogen, 2 atoms of oxygen. Rearranging the equation, we know we can work out that the mass of nitrogen dioxide will be the number of moles multiplied by the molecular mass. And that gives us 0.0018 grams of nitrogen dioxide. And we then can convert the grams into micrograms by knowing that there are 1 million micrograms in a gram. So multiplying by 10 to the 6, multiplying by 1,000 gives us our answer, 1,880. So in 1 cubic centimeter of nitrogen dioxide, there are 1,880 micrograms of nitrogen dioxide. And now we have our answer. 1 ppm of nitrogen dioxide is 1,880 micrograms per cubic meter of nitrogen dioxide. I'm going to ask you now to have a go at these calculations by working out how many micrograms per cubic meter are in 1 ppm of sulfur dioxide. And I've given you the same temperature, room temperature, 25 degrees, 298 kelvins, and I've given you atmospheric pressure, typical pressure. And here is the answer. And please, I would ask you to try to have a go at the calculations and either post in the chat for the week if you haven't worked out and you would like me to pick this up in one of our sessions, because I would be very happy to talk you again through the calculations. So please do let me know by posting in the chat or sending me an email how you get on with this calculation, and if you want me to do this in one of our sessions. Finally, a bit of additional reading, a couple of pages, brief, standard units of measurement that covers roughly what I've been covering in this presentation and talks about typical units for water, soil, and air pollution. So I will stop sharing my screen now, and I hope this was useful. Stop the video and look at it several times, and please do let me know if you want me to work through these calculations in one of our sessions. So thank you very much for watching, and I hope this was helpful.